So our next talk is from Nnadozie Onunkwo Meyerhoff, and he is an M14, and he's at Purdue University, and he is going to tell us about the use of DC electrical circuits to improve chronic neuronal recordings from intracortical electrodes. So we got a technical talk here, and it's all yours.
Well, good morning, everyone. My name is Nnadozie Onunkwo. As I said, I'm an M14. I graduated with a degree in computer engineering. Now, some of you might be wondering what I'm doing here. When I graduated from UMBC, I got to the point where I was just sick of programming. I took absolutely no biology classes in undergrad, and I just thought that I needed to change. So I started to look out into different schools, and I just saw the field of neuroengineering as something that would be something I could still use my computer engineering skills, but using it in a different way. So what exactly is neuroengineering? It basically uses both neuroscience and engineering methods to do two things. You can either use it to analyze different neurological functions, or you can use it as solutions to problems with neurological disorders or limitations. My lab concentrates more on the latter, which is to use them towards solutions to neurological disorders. We more use those for potential for people who are paraplegic or quadriplegic. A bulk of my research is to be applied into cortical electrodes, which will be implanted into the motor cortex. Now, two different types of electrodes that we use. The main difference between these, one is the Utah electrode, which is at the top. Second is the Michigan electrode. The main difference is the Utah electrode has recording sites on the tip, but the Michigan electrode has recording sites at 4 different levels on one electrode, so you're able to take depth recordings. Now, the main purpose of these is to record neuronal function in real time to analyze neuronal activity in a specific area of the brain. Now, I had a nice video to show, but of course it didn't work, so I'll just go ahead and explain what it was going to show. There was a young man, this research was done in collaboration with Massachusetts General Hospital, Brown University, and a company called Cyberkinetics, which develops some electrodes. Now, there was a young man, he was injured from the neck down from a knife injury. So what he volunteered to do was have them implant an electrode in his motor cortex and to use that to train himself to learn how to use his brain by thinking about movement to move a computer. So what he did was he was trained to think about moving a computer cursor, so he's able to open up his email, he's able to change channels on his television, he was able to open a prosthetic hand, just making it open and close. So this would show the importance of research like this. So now some may be asking, why do you need to be so invasive? Why not just put a surface electrode on the brain or on the top of your head? It is a lot safer to put an electrode on the surface of the brain, but you'd be recording from a large population of neurons. Your goal is to be as localized as possible. So that would not be the most ideal if possible. With intracortical electrodes, you're able to go into the brain, get to the small area of neurons, so that allows you to have a variety of different recordings you can take to have more control of a robot or your computer. Now, the problem with keeping an electrode in the brain for a long period of time, of course, as you implant, you injure neurons, which will create an area of neuronal cell death, which would decrease your signal-noise ratio, which is what you want to keep as high as possible when you're taking these recordings. And as with any injury to the brain, you have an immune response. So you have astrocytes coming to that injury site trying to protect the rest of the brain from this foreign object. So the increase of cell membranes around the electrode will increase your impedance over time, which is not what you would like when you're trying to record voltages, just from Ohm's law, V equals IR. So what we decided to do was to analyze this impedance in a rat model. We used the Michigan electrode, which has 16 sites, 4 on each shank, and we wanted to see the impedance over time. Will it increase as prior research has shown? And we just wanted to see what would happen. So by using box and whisker plots, The main thing to look at is the red line is the average impedance over all 16 sites. And you can see that between day 1 post-implant up to day 24, the impedance doubled over time, which is not exactly what you don't want. So from there, we wanted to see what are some solutions to try to reduce this impedance and impedance increase and reduce the signal-to-noise decrease. So there have been different experiments using DC electric fields, both in vitro and in vivo, to induce directional growth of neurites over time. They've been using mammalian cells such as mouse neuroblastoma, and what is most applicable to my research is in the rat hippocampal neurons. There's also been work done in humans using DC electric fields in the spinal cord of injured people injured just through normal injuries. Also been done in dogs and guinea pigs. And what was found that by oscillating your electric field every 15 minutes for over a year, humans were able to regain motor and sensory function. So we hypothesized that we can use the same approach in the brain to induce directional neurite growth over time. So we started with our in vitro model, culturing E17 neurons from rat embryos just to see how our neurites would grow over time. So we began by just doing simple culturing experiments for a day just to see how our neurites looked. Just for our comp Bs in the building, those are neurons up there with neurites growing from that circle in the middle. So important things to see with the electric field. We had an electric field of 10 millivolts per millimeter for about 16 hours. Now, the important things are our neurites. They got a lot longer, and they're more, some of them have more branches. So they tended to grow towards the positive end or towards the anode of our electric field. We're also able to get some of the neurites to actually turn around as they started growing. So some of the important things is that from prior research, the electric field that was supplied to such as hippocampal neurons, the fields were a lot larger. For our cells, we were able to use a lot smaller electric field to still induce directional growth of our neurites, which is important because the more fields you put in the brain, you're going to be damaging it, damaging cells, damaging the electrode as well by possibly inducing different redox reactions. So those are things you want to avoid by having the smallest electric field possible. We'll then move on to our in vivo model. This is just some of the work we've done by making a simple circuit, which will allow us to supply an electric field to an implanted rat. And we just came up with different designs for the electrode rat pack, if you want to call it that, or rat backpack, which we like to call it. So you can just attach it to a simple a rat harness like this. People actually, you can buy this at PetSmart, and it comes with a leash too. I don't know why, but we didn't use that. But we just wanted to use it to attach our simple circuit, supply the field while they're sitting in their cage, and but we're still coming up with different designs for this. So this is just some preliminary work I was doing over the summer. So that's it. Didn't want to get too in depth, but I just wanted to thank my advisor, Kevin Otto, some of our collaborators, and that's it. I'll open it up to questions. Yeah, there's definitely concern with that. We always use different antibiotics and things to make sure that the rat is not in too much pain. Of course, it's going to be in some pain, but we do take all surgical precautions to make sure that the inflammatory response is not as detrimental to the rat's health as it usually would be if we weren't taking care of it. So. Yes, there is a separate part of our lab which actually does stimulation into the auditory cortex. So I didn't go into too much depth about that, but there's also a video of that where we have implanted rats. They have electrodes implanted in their auditory cortex. So they're trained to do different auditory tasks where they hear a sound and go one direction, don't hear a sound and go another direction. So they're trained on that task, and then we implant an electrode in the auditory cortex, and instead of playing that sound, you just stimulate. And what we found is that they'll do the exact same thing with not even hearing anything. Sometimes they are, but it depends. Every experiment had different signal-noise ratios. I mean, it's like you're more so taking a chance. You go in and look at your signal noise and see, are we close to a neuron, are we not? If not, sometimes you pull back out and implant in a different area to try to get the best neurons. So
why do you think that electricity affects the nerve growth? Is it the neural growth factors in the media, or is the neuron itself responding to an electrical field?
I think it's more the neuron responding to an electrical field. There are some other papers that suggest that their response to this electric field is similar to their response during neuronal development, and also through injury potentials. When the neuron is injured, they'll still emit a small electric field, and those will be used to somewhat communicate with other neurons to induce them to grow towards them. So, in my opinion, I think it's more the neuron responding to the field.
Do you have any other questions? No, thank you.
Thank you.